All right. I want this to be a formal occasion. That's why I was saying, ladies and gentlemen, right? I want this to be formal occasion. All right. In case you haven't figured out, class recording has started, so I know you have. Because, anyway. All right. Last week we spent. In all fairness, you guys can't subscribe. When I post stuff, it will go up. So. All right, last week we started drawing a picture that contained a bunch of orbitals. What is an orbital? Place where an electron probably is, right? An area of high probability of finding an electron, right? But with our understanding that electrons could be anywhere, right? So, we talked about the idea that all of these locations in this picture are orbitals, right? These are all probable locations for electrons. Now, we'll learn hopefully by the end of today that some of these locations are more probable than other locations. That the probability of finding electrons in certain orbitals is greater than the probability of finding electrons in other orbitals. Well, like I said, hopefully by the end of the day we'll get there. But the one thing that we want to do is distinguish all of these orbitals from each other. And that's where we get into the idea of quantum numbers, right? The quantum numbers is a set of 4 numbers that distinguish each orbital from all the other orbitals. Okay? On Friday, we introduced 2 of the quantum numbers. Does anybody remember one of the quantum, or the first quantum number that we introduced on Friday? You all have the outline. So, the principal quantum number. So, real quickly, what does the principal quantum number tell us about an orbital? Basically the energy that it has, right? Or how, or relatively speaking, how much energy it has. We use the lowercase letter n to represent the principal quantum number, okay? Orbitals that are closer to the nucleus have lower principal quantum numbers. What does that mean about their energy? Lower principal quantum number, closer to the nucleus, what does it mean about the orbital or the energy of that orbital? Say it? Lower energy, right? Closer to the nucleus, lower energy orbitals, okay? The second quantum number that we introduced on Friday was the angular momentum quantum number. What does the angular momentum quantum number tell us about an orbital? The shape of that orbital, right? So for the most part, we're going to stick to basically 3 shapes, even though there are 4 possible, okay? S orbitals. What do S orbitals look like? They're spheres, right? Regardless of which energy level they are in, all S orbitals are spheres. Okay? So that might be something that if you are looking to get some more detail, right? All S orbitals are spheres. Okay. Next one we talked about were p orbitals. What are p orbitals? Those are hourglasses. So any hourglass, regardless of what energy level it's in, will be a p orbital. Okay. Next ones are d orbitals. D orbitals are what? Dragonflies. Okay, I don't know if that's not actually why they're d orbitals, right? But so we were referring to them sort of as our dragonflies, right? Or if you want to look at them as butterflies, I don't know, I'm going to go with that. Is that the plural of dragonflies, or is it IES? Right? Okay. I didn't know if that was just for the verb or not. So, but. Whatever. So, what? I guess that's true. And then finally we have F orbitals, which we didn't draw because F orbitals are just there's too much going on there for us to actually draw them. Okay? So the angular momentum quantum number, lowercase letter L, we use that to represent the shape of the orbital. And so going back to some of the pictures that going back to our picture the other day, right? We talked about that this is the first orbital that we drew. N is equal to 1 because it's the closest energy, or it's the closest orbital to the nucleus. It has the lowest energy, but because it's a sphere, L is equal to 0. So the 1s orbital has a quantum number, n equals 1, L equals 0. And then we went up here, right? This is the next energy level. It's a 2s orbital because it's a little bit farther from the nucleus. That's the 2 part. The s part because it's spherical. And when we start putting numbers on it, n equals 2 and L equals 0. remember that they all have to be different from one another. So when we get to this point here, right, sorry, we'll start here. This is a 2p orbital. So n is equal to 2, this is the second energy level. L is equal to 1, because it's a p orbital. But when we go here, right, this is also a 2p orbital. Okay? This one. Come on. Oh, no. It's just, that's my day. I had a rough day yesterday. Like, a bunch of things just did not go correct. Did not go wrong. Battery in my car died, and like, yeah, it just was, it was, what? You had a rough day, you had a rough weekend? Actually, Saturday was lovely, so it was my, yeah, so my Saturday was just fine, you know, so I was kind of sad because I had to winterize my garage, like hang all the bikes up and stuff like that. It's just kind of sad because, you know, summer's over. But it was my mom's birthday this weekend, so we had like a birthday dinner for my mom. And, you know, my mom's birthday is on the 11th, so yeah, I didn't do anything. So
I have the same birthday as your mom and Mr. Turner.
wow, that's interesting. So I did not know that my mom's birthday was the same as Mr. Chitteringham's birthday. So. Yeah, it's like family. Yay! All right, there we go. All right. This is also a 2p orbital. Sorry for that little intermission there. And because it's a 2p orbital, n would be equal to 2 and L would be equal to 1 for that orbital, just like it is for this orbital. So now we've run into a problem where we have two separate orbitals that have a similar energy level and a similar shape, and so these two quantum numbers don't tell them apart. Okay? And that's when we get to our third quantum number, which we call the magnetic quantum number. So first, we use a lowercase letter m to represent the magnetic quantum number. Okay? So, third page, magnetic quantum number. And so here, top of the third page here, top of the third page. We use lowercase letter m, okay? And we talk about distinguishing x-axis orbitals from y-axis orbitals from z-axis orbitals. There are multiple p orbitals in the second energy level. How do we tell one apart from the other one apart from the other one? There are multiple d orbitals in the third energy level. How do we tell this one apart from that one, apart from that one, apart from that one, apart from that one? Okay? So this is what we're doing here. We have if we have two orbitals that are in the same energy level and have the same shape, how do we tell them apart? So we talk about the orientation of the orbital around the nucleus. Is it for p orbitals? Is it the x-axis one? Is it the y-axis one? Is it the z-axis one? And our possible values go from negative L to positive L. It seems abstract, but I'll look at it this time. All right. Do we have this written down? Okay, so let's talk about what it means. Let's go to this picture right here. Okay? I know you guys, so this might be where if you would want to maybe make a quick sketch of this picture down on one of your smaller XYZ axis, down at the bottom of the page, that might be helpful here to kind of get more detail about just these three orbitals to begin with, okay? All three of these orbitals, so we have one here on the x-axis, one here on the y-axis, and then one here on the z-axis, okay? They're all red, and that means that they're all in the second energy level, right? So they all have the same principal quantum number. N equals 2, n equals 2, n equals 2. They're all p orbitals. They all have the same shape. So L equals 1, L equals 1, L equals 1. But they are three separate orbitals, and so we have to distinguish one from the other from the other. That's where M comes in. How many possible values can there be for M here? 3, because there's only 3 p orbitals. There has to be one possible value for M to distinguish all the other ones, okay? So remember that I said that M runs from negative L to positive L. What's L? What is the value for L for all three of these orbitals? 1. So that means that here we can go from negative 1 to positive 1, but what do you have to pass through to get from negative 1 to positive 1? 0. So there are 3 possible values for M in this drawing here. Negative 1, 0, or positive 1. Okay? All right. What do you want to call the x-axis one? Does it matter what we call the x-axis one? Actually, no. Because we're dealing with a three-dimensional picture, right? If we turn our three-dimensional picture 90 degrees, the one on the x-axis isn't on the x-axis anymore. It's on the y-axis, right? Is that, are you picturing that in your head? Yes, no, maybe. Right. So the point here is we don't necessarily have a set pattern as to which one is the x-axis, which one is the y-axis, and which one is the z-axis. We just have to make them all different from each other. Okay? So here's the x-axis one. Jordan, you kind of have your hand up, so you get to decide. Okay? I know you were just stretching, but that's okay. So okay. So Jordan, do you want this one to be -1, 0, or +1? Doesn't matter. Pick one. Okay. All right. So Jordan decided that we were going to make the x-axis value for this orbital +1. Okay. Now let's go to the y-axis. What is the y-axis? Or let's go this way. What can't the y-axis one be? It can't be +1. So what could it be? Could be -1, right? That's fine. We can make this one -1 if we wanted to, right? If we make this one -1, though, what has to be true about the z-axis one? It's got to be 0. It's got to be different from all the other ones, right? So all we're doing here, we're just distinguishing one of these orbitals from the other orbital, even though they're all 2p orbitals. Okay? Good so far. Okay with that? All of these are orbitals. They are likely locations for electrons. But will we find a lot of electrons? Oh, sorry, one last thing before we go on to the next one. Here. S orbital, 2s orbital, right? N equals 2, L equals 0. Okay? We said that our M values can run from -L to +L. What's the L value assigned to an s orbital? What's the L value that we assign to an s orbital? So if you run from 0, -0 to +0, how many numbers is that?
0.
Well, because you can't, there's no such thing as -0 or +0, right? There's just 0, okay? How many spheres do we have in each level? Is there ever more than one sphere of the same color? No. There is only one possible s orbital. So for s, right, if L is 0, M has to be 0 as well, because it has to, there's only one s orbital. So it has to be the same for s orbitals. Okay? Go get it. Face you were making this slow. Yes, Kendall, go ahead.
So then why for
Dragonfly? What?
the hourglass.
Okay, for hourglass, okay.
For the hourglass, since the L is 1 multiplied.
So here, when L is 1, right, that means we could have a -1 value. You could have a +1 value, but to get through from like on a number line, to go from -1 to +1, you have to pass through 0. Does that make sense? Are you okay with that for starters? Okay. So here, this was oh, not this one. Okay. So here, here's a dragonfly. Here's a dragonfly. Okay. I moved them off in the middle, but they're two separate orbitals, right? They're both blue, yes? Okay? All blue orbitals have a principal quantum number equal to 3, okay? What shape are they? They're dragonflies, right? They're d orbitals. All d orbitals get an L value equal to 2, okay? Now, Kendall, applying that idea, right? Possible M values go from -L to +L. L is 2 when we're talking about dragonfly orbitals, right? So the lowest possible value for M would be what? -2. The highest possible value for M would be what? +2. But now, let's go through the progression, right? To get from -2 to +2, like on a number line, right? We would go to -2 to what? -1. Then from -1 to what? 0. Then from 0 to +1. So, right? How many possible values are there for M? 5. Take a look at your outline. Second page down at the bottom. Second page down at the bottom. This chart right here, how many d orbitals are there? 5. Here, how many possible values for M are there? 5. Because we got to tell all 5 of those d orbitals apart from each other. Okay? So that means this one, right? We could make this one +2, right? And then for this one, what could it be? What could M value be for that one? -2 or -1 or 0 or +1. Anything that isn't +2, just so we can tell those two d orbitals apart from each other. Okay? This is where it gets pretty complex, right? And again, I'm not expecting you to be an expert in this right now. I want to introduce the concept to you. We're just trying to distinguish all the orbitals from each other. Okay? All right. One last number, and we call that the spin quantum number. Okay. We use the lowercase letter s to represent the spin quantum number. Orbitals are likely places for electrons, but we said there were two big ideas that sort of govern where electrons show up around the nucleus. What are the two sort of goals that our electrons are trying to accomplish? Close to the nucleus, but far away from each other. So any one of these individual spots that we've drawn has a limit to the number of electrons that we will actually find there. And that limit is 2. Every orbital that we've drawn can only hold a maximum of 2 electrons. We refer to that idea as the Pauli exclusion principle. And therefore, we have 2 values that we use to distinguish these electrons from each other. We say that they have different spin. Notice spin is in quotation marks, all right? It doesn't mean that the electron actually spins one way and one spins the other way. It's a way of telling apart the 2 electrons that are in that same electron, or in that same orbital, okay? And we can only have 2 possible values for the spin quantum number for S because there's only a maximum number of 2 electrons within that orbital. Okay? Good with that for now. I know that was really brief on the last one, but there's a reason why, so I want to talk to the next one. Good there? All right. Pull out the outline that I gave you today that says orbital filling up at the top. Oh, not that one. No, we didn't. We can go back to that. Here, let's go back to that. Sorry, everybody. I forgot that I skipped some parts for you guys. So let's go back to the bottom of page 1 and the top of page 2. Let's fill out all the different sections there about energy sublevels. Oh, it's only second page. Okay. So did you get the? Okay. Okay. So the first sublevel that we get to. Sublevel is basically a fancy way of talking about the shape of the orbital. Okay. So the first sublevel we get to is called the S sublevel. S orbitals are all spherical orbitals. Okay. So in each level has an S orbital. It's the first sublevel that we get to. Okay. These are all our S orbitals. Okay. The next sublevel that we get to we call the P sublevel. Okay. Notice you said that P orbitals have what shape to them? All P orbitals are what shape? Hourglasses, right? Notice that the hourglasses don't show up until we get to the red on my drawing, right? The first level, there are no yellow hourglasses. Red is the first level where hourglasses show up. Okay, so every principal energy level from 2 on up has a P sublevel, and that means we have P orbitals. And these are what our P orbitals look like, right? They look like hourglasses. One on the x-axis, one on the y-axis, one on the z-axis, okay? The sublevel basically describes the shape of the orbital, okay? So S sublevels have orbitals that are spherical. P sublevels have orbitals that are hourglass shaped. D sublevels have orbitals that are dragonfly shaped, right? It's the third sublevel. And then finally, the F sublevel is the fourth sublevel. Don't worry about the shape of those because it's no rhyme or reason. Is that good? Well filled in? All right. Good? Okay? Okay. Even though all of the things on this drawing are orbitals, they are places statistically that we're more likely to find electrons than others. Not all orbitals are created equal. There are certain orbitals that are more likely to find electrons in there are certain orbitals that we are more likely to find electrons in than other orbitals. What's going to govern which electrons, or sorry, which orbitals get filled up first? Energy, right? Specifically what? What did we say? Caleb, do we want higher energy or lower energy orbitals? Lower energy orbitals, right? Lower energy orbitals get filled up first, and that means they're closer where? To the nucleus, okay? So, we're going to start off on this diagram here, or this outline here. I know it's kind of boring with just the white background and the black writing, but we're not actually going to take that many notes. We're actually going to draw some more pictures than anything, okay? So, orbital filling. Orbital filling is governed by something that we call the off-bow principle. Okay? Off-bow principle. Off-bow principle states, orbitals are filled from lowest energy to highest energy. And as we've already discussed, which of our orbitals have the lowest energy? Well, where are they? Where are orbitals that have the lowest energy? Closer to the nucleus, right? So basically, we fill up the orbitals that are closer to the nucleus first, and then we go from there. Okay? All right. Good? So we fill orbitals from lowest energy, highest energy. Orbitals closest to the nucleus get filled up first. Then we move a little bit farther out, then we move a little farther out, and we fill them in order of low energy to high energy. Okay? All right. Here's a graph. There's actually two graphs here. Both of these graphs actually show the same thing. I'm partial to the one on the left, so I will use that one the most. Okay? But I think it's a little bit easier to read. Okay? Y-axis, left-hand side. What does it say? Increasing energy of electrons in orbitals. In which way does the arrow point? Up. So if it's an increasing energy and the arrow points up, where are we going to start reading this diagram? At the bottom. We want the lowest energy orbitals first. What's the lowest energy orbital that is labeled on this diagram? 1s. Where is the 1s orbital on our big picture that we drew in the last outline? The middle. Closest to what? Closest to the nucleus. Okay? So, this chart will show us which order orbitals get filled up in. And we will go through and read this chart, make sure we understand how we get from one place to the next. Orbital diagrams. Orbital diagrams show the distribution of electrons within our orbitals. All of the things that we drew in the previous picture are orbitals, but you will find that in a lot of cases, those orbitals are not filled. Yes, they exist, but there aren't electrons in them. An orbital diagram shows us exactly where those electrons are. Depending on what book you read or how you do it in class, I will actually show you a couple different versions. All of them are equivalent, but we will use circles or lines or boxes to represent the different orbitals themselves. And then we will use arrows to represent a single electron. And so, like I said, depending on what book you have, sometimes you will see orbitals drawn as circles with arrows inside of them, like on the left-hand side here. Sometimes you will see them just as lines with arrows above them. I usually go with the one on the right, the one with the lines and the arrows above them, because it's a lot easier and faster to draw them. But either one of these we can use to represent an orbital. Okay? Good for starters? All right. Let's start off with the simplest orbital diagram that we can make, and that's an orbital diagram for hydrogen. Okay? First thing that we have to do when we're talking about a picture that shows us where electrons are is identify how many electrons we have to place. how do we know how many electrons we're going to actually have to account for when we're making an orbital diagram? What tells us the number of electrons that an atom has? The atomic number. Technically, the atomic number tells us the number of protons, but what has to be true about protons and electrons? Have to be the same. Say again. We will see in a couple chapters from now, Ethan, that isn't always the case. Sometimes atoms will either gain or lose electrons in order to make things better for them, okay? So at this point, they have to be equal, but that will not always be the case moving forward, okay? All right, so let's draw our first orbital diagram. I realize time is running short, but this doesn't take very long. So here's hydrogen, and you'll see that at the top of your outline, or no, it's at the bottom of the first page. Okay, you have a little space down there. Okay? First thing we have to do is we have to draw an orbital. So I'm just going to draw one line that looks like this to represent my orbital. We said you can also draw a circle, or you can draw a box. Totally up to you. Now we have to label that line. Electrons fill lower energy orbitals first. So we go back to our chart, and like we said, what's the lowest energy orbital out there? 1s. And so we will label this line as 1s to represent that orbital. How many electrons do we have to place in this orbital? 1 electron. And so I'm going to use an arrow to represent my 1 electron in that orbital. And there we have an orbital diagram for hydrogen. That's it. Now, it gets a little bit more complex, obviously. Hydrogen only has 1 electron, but we're representing that big diagram that we drew in a shorthand way. And we'll work on that more tomorrow.